In this video, I'm going to derive the estimators, OLS estimators in the matrix form. Now remember, we are doing this for a general k variable, or in this case, I'm going to call it a k plus 1 variable model. I'm calling it k plus 1 just for my convenience. You can call it a k variable model. So the equation in general terms for a k variable or a k plus 1 variable model will be yi is equal to beta naught plus beta 1 times x1I plus beta 2 x2I, etc. beta k times xki plus the error term, which I am calling ei. Now remember, beta naught is the intercept term, beta 1 to beta k are your partial slope coefficients. Okay, and remember, when you say the number of variables in the model, you include all the x variables and the dependent y variable as well, which is why in this equation I said, since we have k x variables or k explanatory variables, it's a k plus 1 variable model including the dependent variable y. Now remember, if we have n observations for all our variables, our equation form would look like this. y1 is the first observed y variable is equal to beta naught plus beta 1, the first observed x1 variable plus beta 2 times the first observed x2 value, etc. beta k times first observation of variable xk plus the error term e1. Remember, the error term represents deviation of the actual observed y from the estimated y value. Similarly, y2 can be written as beta naught plus second observation of x1 plus second observation of x2, and so on, beta k times second observation of xk plus e2. Now this can be written as etc. So the nth observation of y is equal to beta naught plus beta 1 times nth observation of x1 plus beta 2 times nth observation of x2, etc. beta k times nth observation of xk plus deviation or error term en. Now this form of equations can be easily represented, or much more easily represented, if you use matrix notation. So in matrix form, I can write this as matrix y is equal to x times beta, where plus e, where y represents a column matrix of all the observed y values. So its dimensions would be n cross 1. Remember, row comma column or row cross column is the format for the dimensions of the matrix. Similarly, x represents the matrix of the explanatory variables including the value of the intercept term, which is why you will have 1, x11, x21, and so on, xk1, and the 1 continues, x12, x22, xk2, etc. x1, x1n, x2n, etc. xk times n. Now the dimensions of this matrix X is n rows times k plus 1. K plus 1 is because you have k explanatory variables and the intercept term. Your beta is a matrix of the coefficients, intercept term beta naught, and all the partial coefficients from beta 1 till beta k. So the dimensions of this matrix would be k plus 1 cross 1, that is rows comma column. Finally, you also have the error matrix, or the matrix which represents the deviations, which can be written as matrix E is E1, E2 and so on, En, and the dimensions of this matrix is n cross 1. So remember, the matrix form of the regression equation can be written as y equals to x times beta plus e, where all of these are matrices as represented below. Now, if you remember, the estimators, the least square estimators, are based on the principle of least squares. The OLS estimators are based on the principle of least squares, which asks you to minimize the sum of the square of the error terms, where I is going from 1 to n and n is the number of observations. So in matrix form, if I want to represent ei square, it can be written as the transpose of matrix E into the original matrix E. That is, we have a row vector going from E1 to En into the column vector going from E1 to En. So you have one row and n columns over here, and you have n rows and one column here, and the product of it, or E transpose E, will be a scalar with the dimension 1 cross 1. That is, you will get one value if you multiply the matrix of error terms in this manner. Why are we multiplying it in this manner? Because our principle of least squares asks you to find the line of regression such that the squares of the deviations, the sum of squares of the deviations are minimized. Now I know that my original model is y equals x times beta hat. Remember, the hat means it's a matrix of the estimated coefficients plus the estimated error matrix. So here E can be written as y minus x times beta hat. Remember, all of these elements are matrices, right? So when we are finding out E square, which is E transpose into E, I can write that as y minus x beta hat transpose into y minus x beta hat.